Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day. So in this video, I'm going to start with the metric space, which is the first week of our study. So previously you have looked some of the inequalities, Minkowski inequality, and also Schwarzschild inequality. So those inequalities actually we need to prove, or we need to use them in order to prove a certain space is actually the metric space. So this is what we are going to study, or this is what we are going to cover in our syllabus. So let us look what is the definition of a metric space. So basically a metric space is a space, a pair of set of where you collect some element in the set of X, and then within that element we are defining a matrix on that particular set of X. So here X is a collection of elements, so we call it as a set, and using those elements we are going to define a metric. So usually in the real number we define the the matrix as a distant function on X. So this is we call it in the real number, but in general we call it as a metric. So therefore this kind of matrix on X must satisfy these four properties. Then we can call it as a metric space. So the first properties is that the matrix on X and Y for any element of X and Y in the capital of X must be more than 0. And the second properties is that it has to be equal to 0 if and only if X must be equal to Y. For this particular statement, you need to prove two ways. So first one, you need to assume the matrix of X and Y equal to 0, then it is implied X must be equal to Y, and the other way around, you start with the X is equal to Y, then you need to show the distance between them, or the matrix between them must be equal to 0. And the third property is that it has to satisfy the symmetrical properties, which is when you take the distance, or when you take the matrix between X and Y, it has to be equivalent to matrix of Y with X. And the last one, the most difficult part that we want to prove in a metric space is this one. So whenever you have the distance, or whenever you have the matrix between X and Y, it has to be less than summation between the matrix X to Z together with Z to Y. So this one you can write either Y to Z or Z to Y. So in certain book, it will return distance of Z to Y, or the matrix between Z and Y. So some books will simply write XD is simply written as X. Here in the case of where we already know the standard matrix defined on the certain space of X. Okay. So example of metric space, let us consider X as a set of all real numbers. So where we define the distance between X and Y, or the distance between 2 points or 2 elements in real number, as the distance, or what we call here, the distance between X and Y. So it means that we are going to take the difference between X and Y, and then we take the absolute value. So actually we are calculating the distance between point X to point Y. Okay, so in order to show that the space of R and D here is a metric space, what we need to do is we need to show it has to satisfy all these four properties. So the first properties is that the matrix defined must be positive. So here we see that we are defining the matrix by using the absolute value. Based on the definition of absolute value, we know that it is positive. So therefore, the first properties is satisfied. So the next properties is that the matrix of x and y has to be equal to 0 if and only if it is x equal to y. Like I said before, it has to satisfy two conditions here. The first condition is that we start from the matrix x y equal to 0, then imply x must be equal to y. So now this is the first condition. So we start with the or we are assuming the distance or the matrix x and y equal to 0. So if we assume this is true, it means that the absolute value of x minus y must be equal to 0. So this can happen if and only if, or this can happen if x must be equal to y. So we already proved that from here x imply equal to y. So next one, we are going to start with the x is equal to y. So in this case, when x equal to y, of course x minus x here is going to be equal to 0. So therefore, the matrix of x and y here, x and s x and x must be equal to 0. So the third properties is symmetrical properties. So we start with the matrix x with y, which is equivalent to absolute value of x minus y, and this one is also equivalent to y minus x, which is a matrix of y with and x. So this is a typo here, should be the matrix of y with x. Okay, the last one is the triangle inequality. So we are going to start with the matrix of x and y, which is equal to absolute value of x minus y here. So in this case, I'm going to add a dummy. So plus z minus with z. So here we are going to rearrange in such a way x minus with z plus with z minus with y. So because we are dealing with the triangle, we are dealing with the real number, we know that the real number satisfy the triangle inequality from here to here based on what we already learned previously. So therefore this part or this absolute value is equivalent to the distance or the matrix of x and z, and this part is actually the matrix of z to y. So because we already showed the third properties, we also can write distance of y to, or the matrix of y to matrix of y with z. So we already proved the triangle inequality. So therefore, it satisfies all these four properties. So we can claim that the set of real number with the distance here is actually a matrix space. Okay, so the next question you can ask me, can we have the same set but with a different matrix? Because this matrix is, we are defining them. Yes, the answer is yes. You can define the matrix as you like, but in order to become the matrix space, you have to show the matrix that you define has to satisfy these four conditions. If it is satisfied these four conditions, then you can claim that your space is a matrix space. So now let us continue with the second example. So this example is much more simple, and the element that we consider is not is a finite element here, where the set of element for x is composed of integer from 1 to 5, and the distance between x and y we define 0, 1 like this. So it is equal to 1 if x does not equal to y, y it is equal to 0 if x must equal to y. So now the task is to show that x, this space x and d is a matrix space. So the solution as follows. So first of all, I'm going to take any value of x and y inside the space capital X here. So when I compute the distance between or when I compute the matrix between x and y, of course I'm going to get more than 0, because I know that the value for matrix x and y must be either 0 or 1. So it depends on the value of x and y here. So the first properties is satisfied. Next, I'm going to consider the second properties. So the second properties, I start with the x equal to y. So I assume, because in the second properties, we need to show two ways here. So we start from the distance, we start from the matrix x y equal to 0, then imply x equal to y. So now I'm going to start from x equal to y first, imply the xy equal to 0. So now I assume that x equal to y. Then I will get, based on the definition, the matrix between x and x must be equal to 0, which is what I want to prove. Okay, now I'm going to start with d of xy equal to 0. So d of xy must be equal to, if I suppose that d of xy, or the matrix of xy, equal to 0, then I'm going to get x must be equal to 1. So this is true because if we say that x does not equal to y, then it implies that the matrix of x and y must be equal to 1, which is a contradiction to early assumption. So the early assumption is this one. So we already assume this is to be true. If this is not the case, if x does not equal to y, then we are going to reach a contradiction here. So therefore, the only possible way that we have to, if we start with x, the matrix x and y equal to 0, must be x equal to y. So now the third properties is that we are going to show the symmetricity here. So to show the symmetric properties, is we start with the x equal to y. Then we will get the distance between them is equal to 0. So therefore, symmetricity here must be satisfied. Okay, so now we are going to, so this case is obvious. So now we are going to suppose the other way around, where we start with x does not equal to y. So when x does not equal to y, then the matrix between x and y must be equal to 1. But this is also true, or this is, the value is also similar if we take the matrix of y with x. So therefore, the matrix of x, y is equivalent to matrix of y, x. So the last one is the triangle inequality. So in the triangle inequality here, also I divide into two cases. So the first case, when we have x equal to y. So when x equal to y, then of course the distance between them must be equal to 0, which is true for n, which is less than if I take the matrix between x and z plus the matrix with y and z here, because the minimum value between these two is 0. So it cannot be lesser than 0, and then of course the maximum is equal to 1. So this part should be could be equal to 0, and this part also could be equal to 0, this one. So therefore this 0 plus 0 should be the minimum value is equal to 0. So this only can happen if x equal to y and y equal to z. So this is only the case, but the inequality still true. And the maximum it can happen is when x does not equal to z and y does not equal to z. Then we are going to get d of xz equal to 1, d of yz equal to 1, which is still true. 2 is more than 0. So now we are going to consider the second case where x does not equal to y. So when x does not equal to y, then the distance between x and y must be equal to 1. So therefore, when we take any z inside the set of capital X here, it could be either z does not equal to x or z does not equal to 1. So it cannot be we cannot have z equal to x and z equal to y at the same time. So because if z equal to y and z equal to y, z equal to x and z equal to y at the same time, so this will imply that x must be equal to y, which is contradict to this assumption. So therefore, it has to be one of them not equal to z. So when we know that the distance between x and y is equal to 1 already. So therefore, when we substitute into this inequality, so the minimum of this part has to be 1. Right. So because x and y cannot be both equal to z at the same time. So therefore, either this one equal to 0 or this one equal, if this one equal to 0, then we will have this equal to 1, or if this equal to 1 and if this one equal to 0, then we will get this part equal to 1, or both can be equal to 1. So when x does not equal to z or z does not equal to y. So in this case, the maximum is 2 and the minimum is 1. So therefore, the distance between the matrix between x, y should be less than the matrix between x, z and y, z. So here we already show this matrix with a defined space here with the defined matrix is actually a matrix space. So now we are going to look a little bit complicated example where we consider Euclidean space R2. So we define the matrix. I think you're already familiar with the formula here. So this is the formula to find the matrix on R2. So now we are going to show that the matrix here with the given space form a matrix space. So here I'm write x equal to psi 1, psi 2, where it is a vector form in R2, and y is in eta 1 and eta 2. So now if we compute the matrix between x and y, so of course it's going to be positive. So this part is clear. So now we are going to show the second properties. So to show the second properties, what we are going to do is that we are going to look on the we are going to assume x equal to y. So when we assume x is equal to y, then we are going to get each of the position here. For example, the first position must be equal to first position of y here. So I mean the first position of x must be equal to first position of y. So therefore psi 1 must be equal to eta 1. And next one, we are going to get psi 2 is equal to eta 2. So with this condition, when we substitute in our matrix, so it has to be equal to 0. So with this assumption, we will get equal to 0, which form or we satisfy the first part of second properties. So next part of the second properties is that we start from, or we assume, the distance between, or the matrix between x and y equal to 0. So when we assume the this part equal to 0, so it means that the square root here must be equal to 0. And luckily we have, or we know that whenever square root equal to 0, mean that it is actually square something with 0. So therefore everything inside the square root here must be equal to 0. That's why we have equal to 0. And from here you have to take note that this square is positive and this square is positive. So how you can add a positive number to get a 0? So of course those two number has to be 0 also, because you cannot have adding two positive number more than, for example, more than 0. You are adding two positive number and yet you get a 0. It's not possible. So of course if you consider positive number, you are adding them, of course both of them should be equal to 0. So therefore we know that psi 1 minus eta 1 equal to 0, psi 2 minus eta 2 must be equal to 0. Both of them are equal to 0. Hence we can conclude here that psi 1 equal to eta 1, psi 2 is equal to eta 2. So with these two conditions, of course it is implied x must be equal to 1. So the symmetrical part is not that difficult. So what we are going to do here, substitute the definition of the matrix here, and then we are going to rearrange psi. So instead of writing psi 1 minus eta 1, we are going to write eta 1 minus psi 1. So this is a similar things, similar value. Psi 2 minus eta 2, we are going to write eta 2 minus psi 2. So this is actually the definition for matrix of y between x. We show the symmetricity of the matrix. So last one is that the triangle inequality. So the triangle inequality, we are going to use the Minkowski inequality. So let us recall the Minkowski inequality in for n equal to 2. So Minkowski inequality say that when we have x1 plus y1 square plus x2 plus y2 square, it is actually less than the square root of x1 square plus x2 square plus y square root of y1 square plus y2 square. So in last video I give you in general case for any n. So you can limit yourself n equal to 2, and I ask you to compute for infinite dimension. So you can try that one. So the proof is quite similar. So now what we are going to do, we are going to apply this in Minkowski inequality. So what we are having here is that, so I'm going to take this part as my x1, this part as my y1, this is my x2, and this is y2. So therefore I'm going to add this part with this part. So this everything here should be less than this one plus with this one with the square under the square root here. So same happen here, same rules. So therefore when we look again, what we have written here is that it is actually the matrix of x, z, and this is actually matrix of z to y. So therefore we already proved the triangle inequality. So this part is actually the difficult one, because we need to use the Minkowski inequality. So that's why in my first class I start with the Minkowski inequality, because that will be the most critical part in order to prove a matrix is a matrix space or not, especially for this space. So this is kind of standard space that we learn. That's why we need that kind of Minkowski inequality. So next one, matrix space on Rn. So we are defining the matrix in the following way. It's quite similar, except that we have n dimension here. So we have n tuple. So now the first one I think is quite obvious, and the second one we are going to start with the or we are going to assume with the matrix of x and y equal to 0. So from here we are going to get summation of the square root here, the square root of the summation here equal to 0. So of course this to be square root to be equal to 0, everything inside the square root here has to be equal to 0. So we will get summation of a positive number equal to 0. So that my explanation before, the summation of positive number equal to 0 means that each of the summation here must be equal to 0. So this implies that every k from 1 to n psi k minus eta k must be equal to 0. So this implies that every eta k is equal to psi k. So hence, because each of the tuples here are the same, we can conclude that x must be equal to y. So now your task is to check to start with the x equal to y, then show that the distance between x and y must be equal to 0. So you have to show by yourself here. And last, the third one, the matrix satisfy the symmetrical properties. So this part also you need to prove. So the proof is quite similar with the two dimension. You can follow the same procedure. And the last one is triangle inequality. So to show the triangle inequality, we are going to apply the finite case of the Minkowski inequality, which is I already proved to you. So the finite case of the Minkowski inequality say that whenever we have so the first one, of course, we are going to write the matrix of x and y like this as defined in the equation, and then we are going to put the dummy here where we put the minus zeta k plus with zeta k. So based on the Minkowski inequality, we can divide this part and this part into summation like this. So of course the equality here will become less than or equal like this. So this is from here to here we are using the Minkowski inequality. So this part and this part is actually what we define here. So it is a matrix of x to z, and this is actually the matrix of z to y. So we already proved the triangle inequality for the for this matrix space. Okay, so the last one is that we have a lemma here. So let D be a matrix space on X, then the function. So this is the new function we define D1. So based on the given matrix D here, so from the beginning we already know that the D here is already satisfy the what we call the matrix space. So it means that D here satisfy all four conditions. So now we are going to show that the matrix given or defined in this way is again a matrix. So to show that, first of all we are going to check the positivity here. So of course T is satisfied positive, so positive divided by a positive number, still we get positive, so therefore D1 is positive. And now if we assume D1 is equal to 0, so it means that the numerator here must be equal to 0. So you cannot have the denominator equal to 0. It is only possible to have the matrix of dxy equal to 0. So based on the properties or based on the assumption D is already a matrix space, so D equal to 0 means that if and only if X equal to Y. So the same process we can proceed. If we start from X equal to Y, then we will get the matrix of X, Y equal to 0, then we imply this part equal to 0, so therefore D1 must be equal to 0. So you can write properly. So this is your guideline how to write. And the third one is that it has to satisfy the symmetrical properties. So the symmetrical properties is you can consider by the following way. So X, Y, we start with the matrix of D1 X, Y. So because we know that D satisfy the symmetrical properties, so we can interchange X and Y here in this way, and at the end we will get D1 Y X here. So therefore D1 satisfy the symmetrical properties on the